Pastrana and Bruun, please, with the paper entitled A New Roof Over the Engineering Courtyard, Studies on Pattern and Form. Please. I don't know if Pastrana or Bruun are with us. It's possible that we have not.
Can you hear me?
Wait. Okay, I see Rafael now that is in connection. Rafael, do you hear us?
Yes, sorry, I have some technical issues. Can you hear me?
You're welcome. Okay, you can start. I just introduced you, please.
Thank you, sorry for that. So today I just wanted to, so we are Rafael and Edward, two PhD students from Princeton in the United States. And today I wanted to present to you like our workflow for a design project of a roof. And basically what we want to showcase is the underlying computational design process. So the motivation was to find a ritual roof, and we had a brief, which basically told us that we had to construct a shell structure or a ritual structure in the engineering courtyard of Princeton University. And the side dimensions were about 58 by 51 meters. And the second restriction was that whatever our design solution was, we couldn't exceed the total existing height of the building surrounding by 1 meter. So that was about 17.5 meters. So we looked into some precedents in order to get some inspiration for that. And we wanted to create like this sort of skin that could host some recreational and educational activities underneath. So for example, this is one project by Foster and Partners done at the Smithsonian Museum. And then we grabbed inspiration as well from these tree-like structures by Shigeru Ban. So we tried to somehow draw parallels and create a tree of engineering life as well, but in Princeton. So for that, we jumped into trying to derive a form that wasn't drawn, but actually found. And we relied heavily in computational pipeline, and we used the Compass framework for that, which is an open source Python infrastructure for engineers and architects. I hope that more than one of you have heard of it before. And here you see, I give you already a sneak peek into what the final solution or the form finding process was using this methodology, where you can see that using a dynamic relaxation approach, we could have colorful, visual, and interactive feedback of the design process. So without further preamble, I just jump into sensitivity study we carried to arrive at our final design solution. So we used a simplified linear model where we used, in red, you can see what the support conditions are, so our boundary conditions, and with the little green arrows pointing downwards, you could see what the load assignments were. Here you see what the response of the structure is after the dynamic relaxation process. And we analyzed 3 different configurations of patterns, or say topologies. The first one was like a typical 90 degrees that I guess like for the majority of us is like the default solution to get started. Then we progressed from left to right to a configuration where we flip that grid to 45 degrees. And in a second, I will explain why. And lastly, we applied a subdivision algorithm so that we had like a restricted buckling length, so where we had higher compression forces. And here I just quickly go over some of the results. Here you see what the force distribution is. And of course, because we had existing buildings, what we try to minimize is how much of that forces were being transferred to them. So here you see like the 90-degree solution there. Then you see what happens with the 45-degree solutions, and we have like, visually at least a stressed system or more forces being transferred more efficiently surrounding. But then we still noticed that we had some higher forces going on. So we decided to introduce midpoint so that we had more vertical forces coming to the ground where we could put some new foundations and then minimize what we had around. But perhaps visually you can see that we have at the column base very large element lengths where we had the higher forces, which of course is no good for buckling. So then this is when the subdivision algorithm comes into play, and then you see that we have like this sort of growing pattern that stems from the central foundation where you have more vertical forces, and then around you have like the minimal horizontal forces transferred to the existing buildings. Interestingly, we plotted the the total load path of the four alternatives, and in this graph you see that more or less option 4, which is the selected one in green, looks a little bit disadvantageous here, but the situation here is that for the first study, we didn't limit the total heights of the building or for form found solutions. So this one is actually 10 meters higher than what we were supposed to derive. So when we apply the constraint, you see that the forces dramatically increase, actually in threefold, and this is to find a shallower version of the shell. So when we apply the constraint to all the 4 examples, we see that the green option, which is the selected one, the subdivided one, was actually a reasonable solution to that. And here you see how it looks like when there is a thickness applied to it for architectural visualization purposes. Lastly, I wanted to present the polarization routine we took to cover the grid shell structure. So typically one would say that once you have a form found solution, then you apply a polarization on the structure itself. But instead what we decided to do was to keep the structure intact and then just run the polarization on glass panels themselves. And we were confident about it because we noticed there were references in build around that actually used this as a feature and not as a disadvantage. And this is basically the outcome of that routine applied to our design project. And that would be it. Thanks very much. If you would like to know more about the project, you can click on the link or go to the website written there or contact us via email. Thanks a lot.
Well, thank you so much, Rafael, for the very nice presentation. Very lovely form and form finding. Please, are there any questions about this this topic, this work? Any questions?
Can I have a fast question?
Yes.
Hi.
I wonder what material did you envision to use, Rafael?
Yes, so for the form finding, we didn't apply a specific material. We just used elasticity modulus of a fictitious material, which was 100 newtons, 100 gigapascal. So there was no real material applied to this project.
Okay, thank you.
Thank you so much. Thank you again, Rafael, for the nice presentation.